All right. Good afternoon or slash evening to those audience, join us over Zoom. So for those who don't know me, my name is Vincent. Thank you for the two great talks from Professor Zerpa and Professor Ko, all the way from Colorado. And thanks for them for sharing their both experimental and modeling work so that we can understand hydroformation and what they have been doing from all over the other side of the globe. So now if I may shift your attention to hydrate nucleation. So what we have done here is probabilistic measurements of hydrate nucleation, and perhaps some of the new data sets that I'm going to show you in this talk would help shed some light on risk-based design for your hydrate management strategy. So just starting off with my personal background. So I graduated as a Bachelor of Chemical Process Engineering at UWA in 2015. And in my final year of study, I did an internship in SPD Group, Schlumberger. And back then, I started to learn how to use OGA, and that's why I have been exposed to the field of flow assurance and gas hydrates. And I was interested to do a PhD back then. So, hence I joined this project, probabilistic hydrate formation risk. And with those data sets that we've obtained from this HPS-ALTA, which is a novel experimental technique that we can generate lots of data sets. And we have been able to verify some hydrate-specific nucleation theory, as well as to investigate the performance of KHI on hydrate nucleation. So really, about 4 to 5 years ago, when I first started in 2016, I was playing with those two mini cells. And the reason why we call mini is because it is really small in volume, about 3 mil. And then since then, we have been steadily scaling up the system from 3 mil to this generation 2 or Gen 2 HPS-ALTA, which we have 20 of them to 10 mil in terms of both volume and higher pressure as well. So can go up to 200 bar. And since the start of last year, we have developed an even bigger system, which can go up to 54 mil and 350 bar. So the focus here, the final goal really is to look at whether can we actually, deploy the experimental data sets that we obtain from these mini cells, and then can it be applied to the industry? So there are 3 main takeaways that if you can take home with you today from this talk, that'd be great. So firstly is HPS-ALTA. It enables rapid mapping of hydrate formation probability and how we can, deploy these data sets in the industry. We have validated some hydrate-specific nucleation models, as well as we can screen inhibitors chemicals very efficiently, such as MEG and KHI. So we have done some experiment in uninhibited system, and then if we add MEG into the system, we found that it actually does not affect hydrate nucleation. In fact, it acts purely as a thermodynamic hydrate inhibitor, such that it shifts the phase equilibrium, and that's it. And in contrast, if you have KHI in your system, it shifts and narrows your hydrate induction time distribution such that it delays nucleation as well as it suppresses growth. So the main motivation of this project really is to look into nucleation. And the conceptual pictures, the top and bottom gas-dominated system, this is drawn by Tom Charlton in his thesis, and the oil-dominated system originated by John Boxall. So there are 2 different types here that I'm showing you, although there are different stages that they are going to. And what industry cares about is you don't want your system to plug, right? So that's the angle. You want to prevent that. And obviously there's a few different stages as well. And Max and Professor Ko have talked to you about the agglomeration process, where you can investigate the cohesion force between hydrate to hydrate particles or hydrate particles to a substrate such as thermoplastic material or carbon steel. But the precursor really here is the nucleation, because without hydrate nucleation, you won't even have to worry about plugging. So hydrate nucleation, in the traditional method, we would inspect if you're gonna get some sort of risk of hydrate formation by looking simply at this phase diagram. So pressure versus temperature, I'm sure all of you are very familiar with this diagram. And this is the hydrate equilibrium curve or dissociation curve. So if you have a system, you want to ensure that your system, you operate within the wide region so that you don't get any probability of forming hydrates at all. But unfortunately, if you have a system that goes and that penetrate through your hydrate stability region, what you would do traditionally is to add THI, such as MEG or methanol. So here, if you add 25% weight of methanol, it can shift the hydrate phase equilibrium region quite significantly. As you can see, the subcooling, the extra subcooling that you're gonna get is about 6 to 8 Kelvin. But however, if you choose to inject methanol or MEG into your system, often the amount is actually directly proportional to the amount of water that you have in the system. And often the amount of injection that needs to completely prevent your hydrate formation can be up to 80% or even 100%. So that's a lot. And then you also need to think about your regeneration system, right? To regenerate so that you can cycle through the regenerated MEG back into your system. So, or you can think about or choose this risk-based method because we know that even if you operate your system within the hydrate stability region, there is some sort of probability that you are gonna get hydrate formation, such that how long do you need to wait? So for example, if you have a pipeline that goes through very deeply into your hydrate phase region, you have a very, very high subcooling. That's a very high driving force for your hydrate to form. So hydrate might form immediately or in minutes or immediately, boom, it just formed. But let's say that if you have your pipeline that just penetrates through just by a little bit, so you have a very low driving force, low subcooling, hydrate may actually form. It may take hours or days to form. So if that's the case, then you need to think about your residence time. So how long are actually the fluids sit within the hydrate stability region? Is it in the matter of minutes, hours, or days, right? So that is the question that we need to ask ourselves, right? So we can then generate experiment in the laboratory and compare those induction times with your residence time. So we want to ensure that hydrate induction time is much longer than your residence time. And then we can be more confident that you can operate within the hydrate stability region without any risk of getting hydrate plugging. But it is actually not easy to obtain meaningful or high fidelity, statistically significant hydrate formation data set. Why is that? Because hydrate formation is stochastic. As I've said, sometimes it takes minutes, sometimes it takes days. So it really depends on which region that you're operating as well. How big is your driving force? So we need to have robust measurements to actually inform induction time and then compare to the residence time. So here's an example of the measurements that I've taken out from our HPS-ALTA experiment. The y-axis is the probability of forming hydrate, and then the x-axis is just simply time. So here, if we operate at a 6 Kelvin subcooling, then you're gonna get this probability curve. So, and this curve is generated by using 100 formation events. So it's kind of smoothish, and then we can then fit to the nucleation model as well. And as you can see, with just single subcooling, the same experimental condition, sometimes hydrate may form in 5 minutes, and sometimes it takes 5 hours to form, right? So, but bear in mind that if you choose to use autoclave or rocking cell to actually run this type of experiments, you can run it, but it may just be kind of time inefficient to generate all these data sets, because typically if you choose to use autoclave, you get about one data or one hydrate formation event one hydrate formation event. So if you want a smooth probability curve, this is 100 formation events. You may take 3 months to actually get one single experimental condition. But we don't want that, because obviously we want to expand out our matrix in terms of different types of inhibitors, different KHI loadings, etc., etc. So here at UWA, so when I first started, we have looked into hydrate nucleation and able to generate lots of hydrate nucleation data sets by using this piece of apparatus, HPS-ALTA. So once again, we started off with generation 1, very, very small mini cell. And then we expanded to Gen 2, about 11 mil, 170 bar, 150 bar. And the data set I will be showing you here, it's actually all from the Gen 2 cell. And recently we have also generated Gen 3, which is high in volume and pressure as well. So looking closer into the cell, this is the top view of the cell. So typically we start our measurements by putting in one magnetic stirrer, and then we put some liquid in. It can either be deionized water, crude oil or some condensate, and then we close the system, seal the cell, and then inject with some high pressure gas, and then isolate it with a valve. And then we place our ALTA cells on top of magnetic stirrers so that the stirrers can generate some sort of shear inside your system to mimic the turbulent system in the pipeline. And then we have got 20 of them of this generation 2 cells. We place them and run experiments within a thermal enclosure. So previously we ran in an oven. The reason why we are doing this thermal enclosure is much cheaper. So to actually ensure that the ambient temperature is controlled, as well as to minimize condensation when the temperature gets too low. So once again, the reason why we're using these cells to generate hydrate nucleation data sets is because of its very efficient heating or cooling rate. So it's up to 5 Kelvin per minute compared to a traditional apparatus such as autoclave. You have on an order of magnitude of Kelvin per hours. So there are 2 modes of the experiments that we can look into to investigate nucleation. The first mode is to see how cold can you get into the region before you start to see hydrates. And that is when we obtain subcooling distribution. And the second mode, which is more applicable to the industry, is instead of saying how cold, how fast would it form? So you cool down to a certain temperature and then wait for a certain amount of period for hydrates to form. So I'm going to talk about the method for both operation mode. So the first mode, once again, it is actually a very quick way. So typically we take about 4 days to a week to get a smooth probability distribution. We start out with high temperature. Then you cool the system down. This black dashed line is your equilibrium temperature. You cool beyond the hydrate stability region. And then when temperature goes down, pressure expansion pressure would drop as well. And then when you see a sudden drop in pressure, that would tell you the formation onset. And then the system will heat back up automatically and before the next formation cycle happens again. So we do this typically until we get about 100 formation data sets, and then, 100 formation events, then we can generate a single data set. And then the second mode, which I've mentioned that this is more applicable to the industry because what we get here is the induction time, how long that you need to wait to form hydrates, and then you can compare it to your fluid residence time. So very similarly, we start off with high temperature, cool the system down, and then you hold it at a rather conservative temperature. Okay, so when isothermally, so temperature constant, pressure would go constant. Hydrate formation onset is once again detected by the pressure drop here, and then you can keep on going and generate more and more induction time data. So for the sake of this presentation, I am just going to focus on the second mode. All the data set I will show you in the future slide is just from the second mode, and it is also more applicable that you can use it in your fields as well. So for those who have attended the tiebacks symposium in the past few times, you may have seen this graph already. So this is just a recap. So once again, what I'm showing you here is probability versus time. And the blue curve is the one that I've shown you in the past few slides, and 6 Kelvin subcooling. So that is from one condition, 100 formation events. So what happened if you increase the driving force? If you operate your system with a higher driving force, higher and higher subcooling, what you will get is you get a decreased induction time. Obviously, high driving force for hydrate to form, for hydrate formation, then hydrate is going to form quicker. And that is for estrus hydrate, which is a natural gas components. So those colored data sets are the experimental data set, and we were able to fit those experimental data set with hydrate-specific nucleation theory. So what I'm showing here is very, very simple exponential distribution. P is the probability, the y-axis. T is the x-axis, the induction time, and T0 is just the mean induction time. So uninhibited system, exponential distribution. And recently, we also have done some experiments with just pure methane system. Very, very similar outcome that we are getting. That for S1 hydrate uninhibited system, exponential distribution. Okay. So what I want to talk to you about here is what happened. What would you expect if you add MEG into your system? So firstly, you can have a look at, once again, this probability versus time. The reason why I have multiple curves here is because, remember, we have 20 cells and we wanted to investigate, is there much variation in terms of cell to cell variation? So you can see that there is, the uncertainty is actually small because it goes from 800 to 1,200 seconds. And once again, 200 seconds plus minus 200 seconds means it may not. It means nothing in the industry. It's 200 seconds, right? So with 3.7 Kelvin subcooling, this is the distribution. And if I draw a straight line on a P equals to 0.05, that is equivalent to a 95% confidence. So we are 95% confident that we can operate the system without getting any probability of forming hydrate for an X amount of time. So, and that X amount of time in an uninhibited system is about 5 minutes. Once again, 5 minutes means nothing to the industry. So now, if you add MEG in your system, what will happen? So if you have been into the previous tieback symposium, so I have presented some results with 5 weight percent MEG, I think. But once again, 5 weight percent may not affect the system much. So here, this is the latest data set that I have added 25 weight percent MEG. So if you add 25 weight percent, imagine if you operate here at the same experimental condition, what would you expect? You're gonna get nothing. You're not gonna get any hydrate formation because it's outside of the hydrate equilibrium region. So say if we run the experiment at the same subcooling, giving the same driving force. So here, this is about 3.7 Kelvin. And here, if I choose to run the system here, which is the same subcooling, what you're gonna get is actually very, very similar distribution. So the induction time distribution in the presence of 25 weight percent MEG cannot be differentiated from your uninhibited system. And it is also exponentially distributed. So what we can say about these, what we can infer from this data set is MEG purely acts as KHI, where it shifts the phase equilibrium curve, but it does not affect nucleation. So the formation probability contour is actually translated with MEG because of this thermodynamic inhibition effect. Okay, so in contrast, what if we have KHI in the system? So once again, this is a base case or uninhibited system. So if you add 0.3 weight percent of KHI instead of MEG, so once again, KHI is a type of low dosage hydrate inhibitors. You need only just a little bit for it to work or for it to delay nucleation. Here I have 0.3 weight percent KHI. So note that the subcooling here is a bit higher. So I had to run it at a high driving force because if I run it at 3.7 Kelvin, I am not going to get any meaningful data such that I will wait isothermally for like 100 hours without getting any hydrate formation. So I need to boost up the driving force where I get some meaningful data with 6.4 Kelvin. So with 6.4 Kelvin, 0.38% of KHI, you can see that it the distribution shift to the right of the graph. So and for an industry benchmark, because it's typically 1 or 2 weight percent KHI. So with 2 weight percent KHI, you can see that the shift of the induction time distribution is even more significant. Okay, so to apply this in the industry, once again, 95% confidence for an X amount of time. And if you draw a straight line here, the 95%, the X amount of time is 2 hours here instead of 5 minutes compared to your uninhibited system. So what we can say about this KHI system is it actually offers a longer period with a very, very low formation likelihood when you operate inside the stability region. Okay, and when you see, when we look into P equals to 0.05 here, that is one thing that tells you. Another interesting information that we can get out from this ALTA experiments is the shape of the distribution, where you can see in base case system, it spreads out from hundreds of seconds to 10,000 of seconds, very, very stochastic. But with KHI, it narrows down the distribution such that you get what, from 8,000 to 12,000 seconds of your induction time, right? So a sharper distribution is actually obtained in the presence of KHI. So here's another data set. So what I've done here is we fix the amount of KHI loading. Here is 3 weight percent. And then we've done the experiment with different subcooling, at the different driving force. And once again, these are all the distributions. And you can see that a nice correlation can be obtained with different driving force as well, depending on how deep you want to operate in your system. So these KHI distributions, the pink line that I'm showing you here, is not exponential distribution anymore, because the sharpen of the distribution makes it non-exponential. However, we can also model it with another common mathematical function, which we found that a gamma distribution is able to do the job well. I'm not gonna talk about gamma distribution, but if you're interested, you can talk to me later, or for those who join over the Zoom, you can leave us a comment, and I'm more than happy to discuss more about how we fit our induction time in the presence of KHI. But in short, we can fit our distribution, and we have a model to describe it as well. So with different subcooling, once again, 95% confident if you operate at a 13 Kelvin, which is a very, very high subcooling. And that is what industry benchmark for KHI not to work, right? So we found that it's about 200 seconds, means nothing. If you lower down the driving force to 9.4 Kelvin, about 20 minutes, you can see from seconds to minutes. And then if you even lower it down even more, 6.6 Kelvin, you get about 2 hours. So the formation probability contour really changed, is quite different for MEG and for KHI. So that was all about hydrate nucleation. Now, does KHI affect growth rate? Because another interesting, the beauty of this HPS-ALTA is we can clearly differentiate the formation onset as well as the growth, which is after nucleation, right? So once again, this is pressure versus time. You cool down the system, you wait for a certain amount of period isothermally, and that is the induction time. In the uninhibited system, no KHI, you're gonna get about half an hour, 0.6 hours, and then the growth we can actually transfer or translate the pressure drop data into your growth rate data, and we can just fit in a straight line here. Okay, and that is the uninhibited system. So what happened if you add KHI? So you can see that if you add KHI, it sits for a longer period, which is 3.2 hours in this case, and then after that, you can see that the pressure drop here is extremely slow. So if you translate that to your growth rate, or initial growth rate rather, so all the black data points here are the data points in uninhibited system, no KHI. You can see that they are distributed around 2 to 4 micromole per second. Obviously, the higher subcooling that you have, higher driving force, hydrate is gonna grow quicker. But with KHI in your system, you can see that it does not only delay nucleation, it also suppresses growth. Okay, and bear in mind that all this data set that we've obtained that I've shown you here today, we have done it in a high mix sync, which is 700 RPM, to mimic the turbulent system when you have a restart or running operating condition. So if you have a system which is a shutdown condition, which all of this probability risk is going to be lower, because the gas to liquid phase mass transfer limitation is going to be high, so it will be harder and harder to actually get hydrate formation. So just want to touch base to the conclusion. So once again, this HPS-ALTA enables us to, it enables us to get lots of high fidelity, statistically significant hydrate formation data sets, and we can validate hydrate specific nucleation models such as exponential distribution, gamma distribution, and so on and so on. And then we can also screen different types of inhibitors. And we've seen that MEG acts purely as a THI. It does not affect hydrate nucleation. And KHI delay nucleation as well as it suppresses growth. So this is a very fruitful research project because there's a lot that we can look at. So apart from looking at gas hydrate nucleation and growth, we can also do some dissociation measurements to generate those equilibrium curve, especially when you have a new field, when there's no data available for multi-flash, we can also do that in ALTA. But one interesting thing is we want to see if nucleation rate scale with system size. So now that we have 3 mil, 10 mil, 50 mil, we want to see that does the nucleation rate really change when you have a bigger system, so that eventually we can scale that up into your part-based system and have more confidence to apply our data sets. The second one is the KHI structure function relationships. So the current benchmark KHI functional group is PVP, and we want to see which KHI perform the best, where it gives us the longest induction time. And the last one, which Bruce has mentioned it as a way forward in his talk as well. So since we we get data set from ALTA experiment. We can then fit the model in, with our experiment. Then can we implement these probability models in flowchart simulation software such as OGA, so that we can then obtain induction time directly in OGA as well, and then compare that to your residence time. All right, so with that, I would like to acknowledge Shell and ARC, Australian Research Council, for their continuous support and fundings. And a big thanks to the team, Team ALTA. So to Research Fellow Peter, Professor Paul, my PhD supervisors, Mike, Zach, and Eric, as well as we would like to welcome and acknowledge two future PhD students who will be starting really soon, Mark Barwood and Chen Long Li. With that, thank you for listening.